Okay, folks, we're going to keep working on these. I'm a little disappointed. It seems that my video quality isn't coming out too nicely. It looks good when I make it, but then when I upload it to YouTube and then you look at it through YouTube, there appears to be some sort of screen resolution issue. So anyway, we'll see. If these continue to be blurry, I'm trying something else now, but if these continue to be blurry, I might put this on hold. All right. Let's read question number 4. Take a minute, pause the screen, read through it. So I think it's helpful to draw a picture to go with this. In this particular problem, what we have is maybe like a conveyor belt that is delivering gravel, and the gravel is forming a pile on the ground. And as you would expect in the real world, this gravel is going to form a conical shaped pile. Okay. Now, depending on something, for those you physics folks know, depending on something called the angle of repose, this is going to form a particularly shaped cone. Okay. Well, in this case, we were told that for this particular material, the base diameter and the height are always equal. Okay. So let's just note this would be what we call the height of the pile. This entire expression right here would be the diameter of the pile, but from the center to just the edge of the pile would be the radius. Okay? So think about it for just a moment. As gravel's falling off and you're starting to form a pile, initially that pile is going to change its height very, very quickly. As you're dumping off, 30 cubic feet per minute, that's a lot of gravel, you're going to form a pile very quickly, and it's going to change its height very, very quickly. But as that pile gets larger, the new bits of gravel fall along, and you're forming a larger and larger cone. Well, it starts to rise less quickly. So the question is, specifically when the pile is 10 feet high, how fast is h changing? That is, our goal is to find dh dt. Okay. So this problem is a little bit harder than the last couple, but it's also, I don't know, maybe a little more realistic. It seems like a more real-world sort of problem. I do want to notice something right now. We'll go ahead. We'll need this in a little bit. Notice that we said that the height is always equal to the diameter for this particular cone. That's not always the case. It depends on the material. Okay, but for this particular cone, the height is always equal to the diameter. Well, remember that the diameter is just twice the radius. So we could say that the radius is the height divided by 2. Keep that in mind because we're going to need that substitution here in a little bit. All right, so remember that our general strategy for these problems is to go ahead and come up with a formula that relates everything together. In this case, we have that the volume of this cone is equal to what? Well, the volume of a cone is 1/3 pi r squared h. Now that's a formula that it might be in your interest to memorize it, but I would give that to you if you need it on an exam. But the way I think about it is, if you put a cone inside of a cylinder of the same height, then it turns out, and I don't think it's completely obvious why this is, it turns out that the volume of this cone is 1/3 the volume of a cylinder. And I did say that you should know that the volume of a cylinder is pi r squared h, and then if you can just remember that the volume of a cone is 1/3 that, you'll have the volume of the cone formula. Okay, so I would like to go ahead and do this. We're going to sort of take a misstep the first time because I don't know that people would always see the initial substitution. So we're going to differentiate both sides with respect to what? With respect to time. That's been the name of the game the whole time for these related rates problems. Okay. So this gives us that dv dt is equal to, now here I have two variables in this quantity, r and h. Careful, that looks a little bit funny. That's an r squared. Let me clean that up. And both are, unlike the cylinder before, both r and h are changing. As this gravel pile forms, the radius of the cone increases as well as the height. So both are changing. Okay. So let's differentiate both, or we've differentiated the right-hand side, let's now differentiate the left. We're going to have to do a product rule. We'll call this the first, we'll call this the second. Okay. So using the product rule, we get the first, 1/3 pi r squared, and then times the derivative of the second, which we'll call dh dt. You are welcome to call it h prime. The biggest thing is just to remember that these derivatives are all time derivatives. Plus, and then on the right hand side, so that was our first derivative of the second, we now get the second, h, times the derivative of the first. So what's the derivative of the first? It would be 1/3 pi times 2r times dr dt. Okay. Now folks, I didn't lie to you in doing this problem. This is, if we didn't know something about the relationship between h and r, this is how we'd have to tackle this problem. If we do a quick skim over what we know what dh dt is. We don't know what the current r value is, but we know the current height, so we could probably find that. We don't know what dh dt is, that's what we're trying to find. We are given the current height. And again, we could find the current radius, but notice we also don't know what dr dt is. Okay, so I could do some complicated substitutions to figure out what dr dt is, but I'd rather go back to the original problem and let's return to this equation right here. The equation that the volume is equal to 1/3 pi r squared h, and let's try to simplify this by eliminating the variable r. Notice that our question doesn't ask how fast is the radius changing, it only asks how fast is the height changing. So in this particular problem, it's nice to go ahead and use this substitution. So the volume of this cone would be 1/3 times pi times h over 2 quantity squared times h, where I just did, in place of r, I put h over 2. Okay. So before we differentiate, let's go ahead and clean that up a little bit. This would give us volume is equal to, let's see, 2 squared puts a 4 in the denominator, so that would be pi over 12 times, and that would give me an h squared times h, so I get pi over 12 h cubed. So folks, if you got lost, just pause the video, expand that out, and see that we get down to this equation here. Now, this looks a lot easier, and when I go to take the derivative of both sides with respect to t, I don't have to do a product rule, so that makes the differentiation step easier. And I'll know all the quantities except for the one I'm trying to solve for. So this would give me, let's see, this would be pi over 12 times 3h squared times dh dt. Let's clean it up just one more step. dv dt is equal to, that would be pi over 4 h squared dh dt, where I combine the times 3 in the numerator and the divided by 12 in the denominator. Okay. So let's take a look up here. We were told initially that the rate of change in the volume, notice this is a volume measurement, it's feet cubed, that's volume, per minutes, that's the rate of change of the volume. We're told that that's 30, and we're asked a question about when the cone has a height of 10 feet. So let's start plugging that into our rate of change formula. We said that this is 30, and that equals pi over 4 times 10 squared, because we said the height of the cone was 10, dh dt. And notice then at this point we know everything except for the quantity that we want to solve for. So that was certainly easier, folks, than when we tried to do this problem without the substitution. So watch for where you're able to use some of those substitutions. Okay, so let's go ahead and finish simplifying this. So this gives us 30 is equal to 25 pi dh dt, or that dh dt is equal to 30 over 25 pi. I could clean that up some, but let's just go ahead and give a decimal approximation. I believe when I checked this, I got 0.382. What are the units on that? Well, let's see here. This is change in height. Height is measured in feet per unit time, and time in this problem was measured in minutes. So at that instant, when the cone when the cone has a height of 10 feet, the height of the cone, it's increasing at a rate of about 0.382 feet per minute. Okay? Where I just got this number by simplifying and giving a decimal approximation of that expression. So let's say it like this: when the height of the cone is 10, the cone's height is increasing at, why is it increasing? Because this number is positive, 0.382 feet per minute. Okay? Take a moment to think about what the situation would be if the height of the cone were less than that. Say the height of the cone were only 5 feet. Would dH/dt, do you think it would be larger, smaller, or the same? How fast is the height of the cone changing if the height of the cone is only 5 feet? Okay? So think about that for a second, and if you have any questions on it, let me know.